Hello YouTube, my name is Gadget Boy and welcome to my channel. This is going to be the first of a few series, anticipating 3 videos, in which I'm going to be building a negative ion generator that is based on something called a Walton Cockroft, or Cockroft-Walton. It depends on who you talk to, it's one way or the other. Cockroft-Walton voltage multiplier that uses an array of capacitors and diodes to increase the mains voltage to a rather astonishing level. And at the very end you have a needle that generates negative ions. It's actually a pretty cool piece of technology. I was inspired to build this by one of the channels I watch. It's bigclive.com. I'll include a link to his channel right here. He's the guy that actually catalyzed me to start my own channel here, so thanks for that, Clive, if you happen to be watching. So here in North America, I live in Canada, doesn't really appear that we have these negative ion generators, and so I'm going to go ahead and build one. Now, let me grab my notebook here. I'll talk a little bit about this thing's a mess. I'll talk a little bit about how this circuit works. Now, it's going to be, do it this way. You're going to have your mains voltage coming in over here. We'll just go with low and high. And it's going to come into a series of capacitors and diodes. I'm going to sketch this out. Yes. Bear with me just a moment here. I'll just sketch out quickly one stage of this neat amplifier, and I'll discuss a little bit about how it works. Now, this circuit is actually very cool. It has its origins actually in early particle accelerators when they needed a very reliable and low maintenance source of high voltage. So this array was developed. Now, your typical negative ion generator, like the ones that you'll see over on Big Clive's channel, they have anywhere from 22 to 30 capacitors and diodes in them. Just because of the way the packaging worked on the capacitors, I'm actually going to build a 50 capacitor version. I've got 2 reasons behind doing it this way. One is because the ones that Clive works with work off of UK voltage, which is 240 volts. We've got 120 over here in North America. And I'm hoping I can make one run effectively without having to have a step-up transformer. I've purchased one, and I'll be testing the effectiveness of the unit with and without the step-up transformer. The other reason I'm doing it is because the capacitors came in packs of 25, and I had absolutely no idea what I would do with 30 extra 100 nanofarad main suppression capacitors. So I figured, what the heck, I'll just use them all, because 1N4007 power diodes are ridiculously cheap. These capacitors, for 50 of them, cost me $10. The 1N4007 diodes cost me $2 for 100. So these are super cheap. Now, back to the circuit. Now the way this works is you've got a waveform that comes out of the wall, and it looks like this. That's alternating current for you. Just your basic sine wave. Now, as the wave, let's see, on this circuit, as the wave is going high, this capacitor begins to charge. And if this capacitor has any charge in it, it actually begins to discharge through this diode and into this capacitor. Then when the waveform goes low, this side begins to charge, and this side begins to discharge into this side as it goes down. So it's basically sort of a push-pull multiplier, and in ideal circumstances, every time one side discharges into the other, you're doubling the voltage. Now, of course, with real components, it doesn't work that way. But the idea is that after, 15 stages, which is what a 30 capacitor Walton Cockroft multiplier is, you're looking at, somewhere between 900 and 1,000 volts, ideally. So it'll be interesting to see what happens with this on mains voltage here in North America. Now, these do suffer a lot from tracking. If you try to do them on a printed circuit board, tracking is where voltage jumps across, from one track to another track where it's not supposed to be going. So we'll be soldering these components together discretely, which is just a fancy way of saying we're just going to solder the leads directly together without any printed circuit board to hold it all together. It's a little bit fiddly to do that, but in this case it's a lot more reliable. Now, one of the really cool things about this circuit is that while it does generate an enormously high voltage, it uses basically no current. It barely registers, if at all, on any sort of current register. So you can run one of these 24 hours a day for pennies, basically. And now I'm sure you're wondering, why would you want to run one of these? The scientific reason would be that the negative ions that come streaming off of the needle at the end of the circuit, they spray out into the air and they stick to contaminants in the air, dust, particles, bad smells, viruses, bacteria, that kind of stuff. And because those particles now have a negative potential to ground, they go and seek out a grounded surface on which to adhere. Now, in the case of the way the circuit is done, the negative potential on this is so high that anything but the circuit itself is basically ground. So in front of one of these negative ion generators, you will start collecting sort of a black sooty substance, which sounds undesirable, but when you consider that black sooty substance is stuff that this thing is drawing out of the air that would have otherwise been in your lungs, it's, worth a little bit of extra dusting from time to time to clean that up. Now there's a bunch of homeopathic theories on negative ions being beneficial for your body and positive ions being bad for you and causing headaches and stuff like that, but I'm not too sure if there have actually been any reliable medical studies as to the actual veracity of those claims. But the effect it has in neutralizing unpleasant odors and pulling dust out of the air is undeniable, because you get very physical evidence of that as your ionizer is running. I'm mainly building it just because I want to see if I can get it to work on North American voltage. But I think I've rambled on enough here, so we're going to move on to constructing this. Now, this is going to be a bit of an experimental thing for me, because I've never actually done something like this. So I'm going to try a couple of techniques to put this circuit together. Well, hopefully the one I've come up with works off the bat, and then I don't have to try a couple of techniques. But you know, if my initial attempts prove to be unsuccessful, I'll move on to a different technique and see where things go from there. Anyway, so what I'm doing here is I'm just grabbing a piece of packing tape here. I'm going to just put that there, and then I'm going to start lining these capacitors up along it. I'm going to put 25 of them down, hopefully reasonably straight. Just like, oh, this is going to be messy. Just like this. I'm sure you guys probably don't want to watch me do all of this, so I'm going to quickly place all of these. Well, I'll time lapse it, but it's probably going to be a really boring time lapse. So either you'll see a time lapse of me squishing these capacitors down onto this tape, or we'll just jump cut to me being done, and we'll continue from there. So I will see you all in a few minutes. All right, and we're back. So that's all 50 of those capacitors lined up neatly. Now you'll notice that I staggered them, and there's actually a bit of logic behind that. The reason for that is because, pardon me as I rummage around for some sort of a knife to slit the tape with. I'm actually going to be soldering these together with a physical arrangement exactly that of the diagram that I wrote earlier. So with the capacitors staggered halfway across each other like that, I'll be able to mount the diodes diagonally across the pins all the way down. And if the component spacing works as I'm hoping it will, it should actually align itself quite nicely and give us a rather neat final product that holds itself together nicely. So now I'm just going to quickly, maybe that's good enough. Probably don't need to slit that all the way down. So I'm just peeling this excess bit of tape away. This tape idea I had actually worked far better than I had hoped. So that's quite a bit heartening there. I did not cut enough tape in my initial bit there. Get this extra bit away there, off to the side. Katie, don't eat it. Katie. Yeah, there we go. Sorry, my cat looked like she was going to either eat or play with the tape there. All right, so Now we have to decide which end of this capacitor network is going to be the mains end and which is going to be the ionizing end. It's very important that you align those in the correct direction, or you'll end up with a positive ion generator, which doesn't necessarily change anything, but these are typically done with negative ion generation at the tip. The homeopaths will tell you that it's because the positive ions will make you headaches and irritable and all of that quackery. Big Clive's theory on it, and I'm with him on this, is that with electrolysis, when you're plating something or electrolyzing a fluid with electrodes, the positive electrode tends to corrode a lot faster than the negative electrode. So there's a potential that a positive ion generator may end up rusting or corroding or having some sort of weird chemically thing happening, at the emission end, which actually might be something that's worth testing at some point. So I'm just going to turn my soldering iron on now and do a quick demonstration of how I'm going to be soldering these diodes in place. Once again, I won't make you guys sit through everything, but we'll do a little bit of, do a couple of them just to kind of experiment with methods of tacking them down while keeping everything neat. So let's get started here. So I'm going to make this be the emission end, and in order to make this be the emission end, the stripe on the diode has to be pointing towards the mains end of the circuit. So we're going to point all of the diodes that way, and this will be our emitting side of it. And over here, if I did that off camera, over here is going to be where the mains plug in. So the voltage way over here off camera is going to work its way through the circuit, and by the time it reaches here, hopefully it's high enough to be emitting positive ion, or negative ions. Correction there. Now, let's see, how do I want to accomplish this? So for now, what I'm just going to do here is we're going to kind of, it's a bit fiddly here. Probably get a pair of needle nose pliers to do this, but we'll just kind of fold this lead down over top of the diode there. We'll grab this, and I actually hope that I can thread it through like so. And this lead, boy, those wires are quite stiff. There we go. And then just to see if this is going to actually cooperate. Yeah, this is going to work. It is worth noting that I did pre-tin all of the leads off camera before I started this, and that's going to help me immensely with actually soldering these together. When you're doing discrete soldering, you want to make sure that everything sticks together with a minimum of effort. And hopefully, with the bit of pre-tinning that I did, I won't have to fiddle around too much with the slippery, discrete soldering connections here. Let's just get this cable for the iron under control here. Now I got myself a new tip for the soldering iron. Previously I was using this one. You'll see it's very pointy. It's a great tip for precision soldering, like when you're working on a surface mount board and you need to get in between tightly packed components. But for this sort of bulk soldering, that tip just simply doesn't have the thermal capacity necessary to make this kind of large-scale soldering job anything but onerous. So I bought myself this new chisel tip, and it has a much higher thermal mass, which is going to make soldering a lot simpler. It's in the tip of it here. There we go. Yeah, that's wonderful. That was basically instantaneous. Okay, this is going to be the entertaining one here. Let's see if we can get in there. That looks pretty good. All right. So that's basically what that's going to look like. And then the next stage would be fitting these in. I'm actually really liking how nice and tight this all fits together. It's all kind of gluing itself together. So I'm just going to cross those leads a little bit to kind of stick it all together. Flow some solder in there, and I'll clean up the sticky outy bits later. Alright, so the diodes are all pointing in that direction. Got nice solid, if kind of messy looking solder joints. So I am just going to proceed to solder these 50 diodes into place. I won't make you guys watch all that. And I guess I'll see you guys in about a year when I'm finished. So I will do a jump cut or a time lapse or a combination of the two here, and see you guys in a little bit. Alright, we're back for a little bit. If I've time-lapsed the work there, sharp-eyed viewers may actually notice when I actually start honing in a technique for putting this whole thing together. I think I've found a method that I'm really quite fond of. I'm just going to quickly show you what I'm doing here. So I'm staggering the diodes inside, actually in between the leads of each of the capacitors. And then I'm taking the leads of, I'm taking those leads and I'm actually wrapping them around the top diode wire, like so. And that is actually creating a very tight initial bond without solder for that joint. And then I'm just tapping it with the soldering iron and flowing some solder, and it fills in there really nicely and makes a very nice joint, very clean for a discreetly soldered joint like that. Then I just went through and quickly trimmed everything off. I'm actually going to be taking a break at this point. You guys won't experience that break because the video is just going to continue after I get back. But I'm actually going to go buy myself a pair of pliers with really fine tips that I can use to make the bending of those leads a little less hard on my fingers. And I will continue from there. I may continue the time lapse, or the video may just blip for me having finished the whole 50 diodes being soldered in. I'm just going to carefully give you guys a close-up here of the resulting product here. Let's get some extra light on this. So you can see the diodes are all... Oh, do you see my rookie mistake there? I'm going to have to correct that one. See that diode? It's pointing in the wrong direction. That is going to be very challenging to fix. So I've got to pay better attention to what I'm doing there. But all of the other ones you can see are oriented in the correct direction. If I hadn't caught that, probably there would have been a loud bang when I started it up. And there would have been smoke and flames and recrimination and tears and yeah, so we'll make sure I fix that. And yeah, I'll come and see you guys in a little bit when I'm actually done the whole thing. So see you in a blip. Alright, and we're back again. As you can see, I've got the whole thing soldered together now. I'll just focus in here. I was very careful when completing it and made sure that every single diode was soldered in the appropriate direction all the way down to the bottom here. So that's what a 25-stage Cockroft-Walton multiplier looks like. Now the next stage will be just soldering on some mains leads on this end of the multiplier. And on this end, I've already soldered on this little thing here. This is just 4 10 megohm resistors. I've got 2 in series, and then those 2 pairs are in parallel. And that's just to provide a current limiting for the circuit in case you should accidentally touch the emitter. It will limit the amount of current that actually goes through your body if you touch one of the emitter needles, rather than allowing you to take the full potential of mains voltage. If you're anywhere referenced to ground, that would hurt a great deal. In this case, you'll just get a bit of a tingle. So that, shut up phone. The next phase will be connecting a lead to this end to the emitter array, which I have yet to design and build. That will be the next video. I've actually already tested this with mains. We got a very nice little ball of corona discharge on the end of the wire there. So it works. So I will continue in the next video with the next part of the project. Thank you for joining me for this. If you enjoyed the video, do that thing you do when you like videos, and I will see you in the next video. Bye.